Welcome to The Explainer. Today, we're doing something really cool. We're literally building a network connection completely from scratch. If you've ever wondered exactly what's happening beneath the surface to pull information from the wider web right down into the palm of your hand, well, you're in the right place. We're going to architect this step by step and analyze exactly how this incredible hardware ecosystem fits together to make our modern digital world possible.
I mean, think about it for a second. How did this explainer actually reach your screen today? You tapped a glass screen or clicked the mouse, and boom, massive amounts of data instantly flowed into your device to produce the high-res images and clear audio you're experiencing right now. We totally take this for granted every single day, but the physical reality of getting this information to you at this exact moment across continents and through complex local networks is absolutely staggering. Because right behind that screen is this complex, perfectly choreographed chain of invisible hardware. And honestly, it's mind-blowing. Every single time you load a web page, send an encrypted text, or stream a video, dozens of physical pieces of technology must seamlessly pass your data along in fractions of a millisecond. If just one link in that physical chain fails or misroutes a single packet, the whole system stops dead in its tracks. The crucial takeaway here is that the seemingly weightless, wireless magic we experience relies entirely on concrete, highly engineered physical foundations. So, to build our network today, we're taking a logical bottom-up approach. We'll start with the physical foundation, move up to internal network connectors, look at directing the traffic, open gateways to the web, and finally finish up with endpoints and going wireless. Setting up this mental map is going to make understanding these technical components a breeze. Let's dive in.
Starting right at the bedrock with step 1, the physical foundation, wires and cables. Because look, before we can even talk about the invisible wireless signals floating through the air, we have to talk about the physical cables carrying the bulk of our data around the world. The cloud is actually buried in the ground, right? We've got two main players here. On one side, copper cables, which use carefully timed electrical signals. On the other side, fiber optic cables, which shoot rapid pulses of light. Fiber is the heavy-duty backbone of the global internet since it handles insanely high speeds over vast distances without dropping the signal. But good old traditional copper, that remains your massive, reliable staple for connecting everyday local devices inside a single building.
And if we zoom in on those traditional copper cables, you'll see a critical distinction. Unshielded twisted pair, or UTP, versus shielded twisted pair, or STP. UTP is your standard everyday network cable. The twisted wires inside naturally cancel out basic interference. And honestly, it gets the job done perfectly for most homes or standard offices. But STP, that's the heavy armor. It adds extra layers of physical foil shielding around the internal wires. So if you're running infrastructure near heavy industrial machinery, dense server racks, or high voltage lines, STP is an absolute must to ensure your data doesn't get scrambled by outside electrical noise. Okay, now that our physical cables are firmly laid down, let's step up a layer to part 2, internal network connectors, our local intersections.
So what are these cables actually plugging into? Historically, the hub. It's a basic device that connects multiple computers together, but here's the major catch. It blindly broadcasts data to all of its connected ports. It's literally the oldest, simplest internal connector we have. If computer A wants to send a private packet strictly to computer B, the hub doesn't know how to filter that. It just yells it out to computers C, D, and E too. It's essentially like walking into a crowded, noisy room and screaming a highly specific message at the top of your lungs, just hoping the right person happens to hear it. Not super efficient.
Which brings us to the much smarter evolution, the switch. Instead of shouting a message to the entire room and causing massive data traffic jams, a switch is a smart networking device that actually learns who is who. It intelligently routes data only to the intended destination. It effectively takes that data packet, walks right over, and whispers it directly into the ear of the correct recipient, completely ignoring everyone else on the network. You can really see the operational difference here. The hub relies on that simple, blind broadcast method, pushing data out everywhere, which pretty much guarantees data collisions and clogs up your network bandwidth with useless traffic. But the switch acts smartly. By directing data strictly to the target device, this targeted delivery method completely isolates the traffic, significantly slashes those data collisions, and makes modern local networks incredibly fast and reliable. Now, switches do a phenomenal job of building out a single local network. But what if you have a group of computers on a switch in one office building and another group in a building across the street, and you need them to seamlessly share resources? That's where a bridge comes in. A bridge is a specific piece of hardware deployed to connect two entirely separate local networks together, literally bridging the physical gap so they can operate and share data as if they were one unified system.
With our local roads and intersections perfectly built, we need a robust navigation system. Let's move to part 3, directing the traffic using addresses and post offices. For data to actually travel smoothly across all these cables and switches, it needs to know exactly where it's going. It uses highly specific addresses to do this, primarily the MAC address and the IP address. Think of it like a house. Your IP address is your logical location on the network. It's exactly like your street address. It can and will change if you pick up your laptop and move to a coffee shop. But your MAC address, which stands for Media Access Control, is the permanent physical identity hardwired straight into your device by the manufacturer. It's like the permanent name of the specific person living inside that house. A network absolutely relies on both to ensure data successfully navigates to the right building and then gets handed to the correct hardware inside.
And who ultimately manages all this? The router. The router is the central hardware device directing data packets between different networks using those dynamic IP addresses. If the IP address is the house address, the router is the local post office of our digital network. It rapidly reads the IP addresses stamped onto your data packets, checks its internal routing tables, and instantly figures out the absolute most efficient path to send that data exactly where it needs to go next.
Which naturally leads us to part 4, gateways to the web, bridging the massive gap to the outside world.
See, your local network is highly organized and beautifully structured right now, but it's entirely isolated. To securely leave your house and merge onto the massive global internet highway, you need a modem. The modem is the essential gateway that translates data between your local router and the global internet infrastructure. Your local network speaks one specific digital dialect, but the massive infrastructure supplied by your ISP speaks a totally different one. The modem sits right on the edge of your network, acting as an incredibly fast translator, constantly modulating and demodulating your local data into a format that can safely travel across the thousands of miles of fiber and copper making up the internet.
And finally, part 5, endpoints and going wireless, cutting the cords.
How does this data actually leap from the network into our devices? Well, for a machine like a high-powered desktop computer to physically receive data, it needs a network interface card, or NIC. The NIC is the vital hardware tucked securely inside a computer that lets it interface with a network via a cable. It acts as the literal physical plug on the back of your machine, where those copper cables we talked about at the very beginning snap securely into place.
But let's be real, most of us aren't plugging physical Ethernet cables into our smartphones or slim laptops anymore. We rely almost entirely on the freedom of wireless. So how does that wireless handoff actually work? Let's demystify the acronyms. It's basically a 3-step relay race. Step 1, your heavy-duty internet connection comes into the building hardwired. Step 2, that hardwired connection hits a wireless access point, or WAP. Step 3, the data is transmitted invisibly through the air to a wireless network interface card, or WNIC, located deep inside your personal device. It feels like effortless magic, but it is highly engineered routing.
Looking closer at that crucial middle step, the wireless access point, this incredible piece of hardware is what allows untethered devices to connect back to a wired network. It takes the solid, hardwired data stream coming from your router or switch, translates it into radio waves, and broadcasts the network completely invisibly through the air, penetrating walls and floors to blanket your entire environment in connectivity.
And to finally conclude our build, catching those waves is the ultimate endpoint. The WNIC, the Wireless Network Interface Card, is a highly calibrated internal receiver that catches those complex radio waves for your laptop or phone. It's essentially your device's dedicated internal antenna. Without a functioning WNIC to decode the signal, those Wi-Fi waves would simply bounce harmlessly off your screen, and you'd be left completely disconnected, no matter how robust the rest of the network is.
So as we wrap up this explainer, I've got a quick challenge for you. Take a second and look around the room you're in right now. Seriously, glance around. Can you spot the invisible handoffs happening to keep you connected? The router quietly routing packets, the access point broadcasting above you, the tiny WNIC receiving data inside the very device you are looking at right this second. We've mastered this physical chain today, but as our global data demands skyrocket and we push relentlessly toward things like quantum networking, you have to ask, how long can this foundational hardware support our invisible demands before it requires a complete architectural revolution? Next time you stream a 4K video, remember the incredible physical journey that data just took and wonder what that exact same journey is going to look like tomorrow.